Hey y'all, welcome back. Today we're going to start a brand new unit on what are known as sequences and series. So for today we're just going to look at what a sequence is. We're going to look at a couple of different sequences and learn how to write equations for sequences in various forms. So without further ado, let's jump right into it. So a sequence is any ordered set that has a first term, a second term, a third term. In other words, it has a bunch of terms that are in a specific order. And mathematically, we can think of a sequence as a function whose domain is the set of positive integers. So basically what I'm saying here is that if you have a function and you look at the table in the calculator, for instance, the default setting is just to show you the values of the function where x is 1, 2, 3, 4, 5. But as we know, most of these functions we're looking at have values in between those integers. So for example, like if you were to plug in an equation into y equals, like let's pull this up real quick, and so I'm just going to throw in a real simple equation like 2x plus 3. If I go to the table, you'll notice that all the values that are given are for integers, right? Now we know that there are values in between here because we don't just have a list of points. When we look at the graph, we can see all the points are connected, so we know there's an infinite number of points in between there. When we talk about a sequence, though, we're only going to have a domain that is just these integers, so and more specifically the positive integers, so starting with 1 and moving forward. Everything else is sort of discarded, and what you end up with is a series of points rather than a continuous line. So that's basically what a sequence is. We write it a little differently. So instead of writing f of x like in terms of x, we'll write a sub n in terms of n. We'll use this little subscript to denote what the independent variable is. And usually it'll be n rather than x. And this is just a convention to remind you that these inputs have to be integers rather than just any old real number. So what I'll often do is ask you to write the first few terms of the sequence. So here's an example of a sequence, 3n minus 2. And if I ask you to write the first 4 terms of the sequence, this is kind of what I'm looking for. Okay, so the first term, if I want to evaluate a function that's written like this, like f of x, I would write something like f of 2 equals whatever to find the value of the function when x is 2. So that input you'll write right down here. So I want to write the first 4 terms of the sequence. I'm going to write it as like a sub 1, a sub 2, a sub 3, a sub 4, and that will correctly notate the different terms. So a sub 1, for instance, let's see if I can make this small on here real quick. Yeah, that'll work. So let's see, get rid of that. So a sub 1 is going to equal whatever I get when I plug in 1 into the sequence. So 3 times 1 minus 2. Probably don't need a calculator for this one. 3 times 1 is 3, minus 2 is 1. So the first term is 1. Okay. So the second term, we'll find it just basically by doing the same thing here, except instead of plugging in 1, we'll plug in 2, and 3 times 2 is 6, minus 2 is 4. The third term, we'll plug in 3 rather than 1 or 2. We get 3 times 3, which is 9, minus 2 is 7. The fourth term, a sub 4, it'll be 3 times 4, which is 12, minus 2 is 10. So the sequence here, we've identified the first 4 terms of the sequence. We're basically done, but a lot of times what you'll see is a sequence written out as just like a list of values. So if I'm going to write the sequence, I might write it like this: 1, 4, 7, 10, and then just do dot, 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 because we know that this sequence continues. We can verify these in the calculator. I guess I just left this up here, my bad on that. But let's go ahead and change this to the equation that we actually have. And we could do 3x minus 2, okay? Now, even though we're putting it in as a function, this will still work. If I go to the table, I'll still be able to find my a sub 1, which is 1, a sub 2, which is 4, etc., 7, 10, 13, 16. So if you know what the explicit equation is for your sequence, it's really simple to find what all the terms are. What we'll see later is the challenge is often not so much finding the terms given the equation, but actually figuring out what the equation is for the sequence just given the numbers. So like over here, if I were to just give you 1, 4, 7, 10 and say, okay, well, write me an equation that would represent that, that's really where the challenge for today is going to come. So let's take a look at how we are going to do that. So there's actually two different ways that we can write formulas for sequences. We can either write them explicitly or recursively. So the main difference between writing an equation recursively or explicitly is what your input is. So what I mean by that is a recursive formula will give you the value of any term you're interested in based on the previous term, while an explicit formula gives the value of a specific term based on its position. So when you're writing an equation explicitly, you write it as a sub n, you write it as a sub n in terms of n. So you have a sub n equals, and then you just have your equation in, oh, well, that doesn't look very good. So you have whatever your equation is in terms of n. In other words, you can just straight up plug in n to find whatever whatever value you're looking for. So if you're looking for the fourth term like we did above, you could just plug in, like this is an example of an explicit equation where you can just literally plug in 4 and get your term. Okay, so it's an equation in terms of n. A recursive formula is one in which instead of plugging in n, you plug in the value of the previous term. So you still write your equation as a sub n equals, but instead of writing the equation in terms of n, you write the equation in terms of the previous term. Okay, so the way that we write that actually is instead of using n, we write it as, get rid of all this, a sub n minus 1. Okay, so if a sub 3 is the term you're looking for, then we are going to find it by using a sub 2. So in other words, you'll just plug in the previous term. Okay, now there's some catches here. When you're writing in a recursive formula, you have to know the previous term. So if you work your way back, you might be thinking, okay, well, how do I actually kickstart this whole recursive equation? Well, you must know a seed value. In other words, some number to kind of kickstart the equation. And as we go through a couple examples, this will probably make more sense. And usually we call this seed value a sub 0. So I know I said previously that the sequences are defined as having as being a function where the domain is restricted to positive integers. And so normally you wouldn't think of a sub 0 as sort of a valid term here. But if you were to sort of work backwards and figure out, okay, well, really isn't an a sub 0, but if there was, what would it be, just based on whatever the pattern is? That value would be considered your seed. Okay, so say, okay, well, I have a recursive equation where I'm going to just multiply the previous value by 3. The way you would write that is you would say a sub n equals, let's see here, there we go, equals 3 times the previous term minus 1, a sub n minus 1. So this is just an example of what one might look like. And so you would say, okay, whatever the previous value is, multiply it by 3. So if the previous value is 1, then your sequence would be 1 times 3 would be 3, times 3 would be 9, times 3 would be 27, and so forth. But as you can imagine, that you have to start somewhere, right? Like this is not enough information to give you the sequence, because instead of starting at 1, if say I started at 2, then my sequence would be 2 times 3 is 6, times 3 is 18, and so forth. So it is imperative that you have what is known as this seed value. So like for instance, with this recursive formula right here, let's say my seed value was 1. If seed value is 1, then the sequence is 1, I'm sorry, not 1, because you got to plug that 1 in. So a sub 1 would be 3 times 1, which would be 3, times 3 would be 9, times 3 would be 27, times 3 would be 81, etc. But if the seed value was, let's say, here, let's just copy this real quick. If the seed value was, let's say, 2, then even though we have the same recursive formula here, where we're multiplying the previous value by 3, our sequence is different. So if I start with 2 times 3 is 6, times 3 is 18, times 3 is, well, what is 18 times 3? I'm going to bust out the calculator here, no lie. 54, and so forth. And so, as you can see, the seed value makes a big difference. Okay, you can have this recursive formula, but without the seed value, it's not going to be clear what the sequence is. So you don't have to worry about that with an explicitly written formula. You know, if I just have, you know, a sub n. Let's see here. If I have like a sub n equals, you know, 3n, now my formula is just okay. Well, you just plug in n, you know, a sub 1, a sub 2, a sub 3, etc. So in this case, I don't need a seed value. My first term would be 3 times 1, which is 3. My second term would be 3 times 2, which is 6. My third term would be 3 times 3, which is 9. And you can just keep going. So you don't need a seed value with the explicitly written equation. And in fact, all the equations you've probably written in your math career have been explicitly written. So this whole idea of a recursive formula is really the new part here. And what we're going to look at are 2 different types of sequences, and I'm going to show you how to write it explicitly and how to write it recursively. Other than classifying our equations as being either recursive or explicit, we can name the different sequences based on their pattern. And like I said before, we're going to look at 2 different kinds of sequences today. So the first sequence we're going to look at is called an arithmetic sequence. And an arithmetic sequence is one that has a common difference. But you should actually, this one is probably the easiest one because you've had the most experience with arithmetic sequences without really knowing it. An arithmetic sequence is really just a linear function where your domain is positive integers. So when you write an explicit formula for an arithmetic sequence, you want to be thinking like it's a linear equation. So like back in the day, you wrote an equation like mx plus b, right? Y equals mx plus b, where you had a slope and a y-intercept, where the y-intercept was the value of the function when x was 0, and then the slope was your rate of change. Well, an arithmetic sequence is written almost exactly like this. In fact, you're going to think that it looks pretty much identical. So let me give you the explicit formula for an arithmetic sequence. A sub n, well, can I get that n on there? Let's see here. I don't know why that subscript always giving me a little trouble here. There we go. All right, that's enough. That's enough. There we go. Okay, so a sub n equals dn plus a sub 0. Now, a sub 0 is not really a term in the sequence because the input has to be 1 or greater. But we can sort of think about a sub 0 sort of in the abstract, thinking, okay, well, if there was a 0th term, what would it be? So take a look at these 2 equations. They look almost the same, right? Our a sub n is in terms of n. Our, maybe I'll write this as f of x, should be in terms of x. But the form of the equation is very similar. So the difference here is that we have d and a sub 0 instead of m and b, but they basically play the same role. The d stands for the common difference. Oops, I don't need any of that. Let's see, where's my shapes? There we go. So the d, which is right here, okay, that is known as the common difference. So that's what the D stands for. And you calculate the common difference just the same way you would calculate slope, change in y over change of x, except in this case it'd be change in a sub n over change in n. And then the a sub 0 you would have to calculate separately. So let me show you how to get both of these. To find the common difference, like I said, it's just like calculating slope. How do you calculate slope? Change in y, y2 minus y1 over x2 minus x1. In fact, let's write that. So in this case, you would have x2, the change in x, divide, hold on here. I'm sorry, the change in y, wow, I'm slipping today. The change in y over, the change in x. So this formula is pretty, I think, well established. You guys have dealt with this many times. Make these little subscripts look nice. And the way we're going to calculate the common difference is basically the same. Okay, it's the same exact idea here. So to calculate our common difference, it will be the change in, well, not y, it'll be the change in a sub n. Okay, so we would say something like, and it doesn't have to be like two ones that are right next to each other. So we can say something like a sub whatever, so I'll call it, let's call it P, minus a sub whatever, we'll call it Q. So you just pick basically two different terms. Let's make those subscripts look a little nicer. There we go. Divided by, so that's like your change in y, divided by your change of x, which would be your change in n. Okay, so that'd be like P minus Q. So whatever like values you have, so if I have like two separate terms, like if I know what a sub 2 and a sub 5 are, I could just plug in a sub 5 minus a sub 2 over 5 minus 2, and that'll give me my common difference. The a sub 0 can be found a couple of different ways. Remember that the b is the y-intercept. In other words, it's the y-intercept, which is the value of y when x is 0. That's basically what the b means. Let's organize this a little bit, a little nicer here and make it easier to look at. Okay, in the arithmetic sequence, same basic idea, except the easiest way I think to calculate a sub 0 is just to find a sub 1 if you can, and then just subtract the common difference. There is an algebraic way to solve for it, and if we come to a problem where we need to do that, I can show you that. But in general, usually the easiest thing to do is to say a sub 0 equals a sub 1 minus the common difference. Now, if we don't know a sub 1, we might have to change gears a little bit, but that's how you're going to find that a sub 0, which is basically playing the role of the seed value when we get to the recursive part. Okay, so let's take a look at the recursive formula. I wonder if I can just kind of shift all this stuff over. Oh yeah, there we go. Okay, so for the recursive formula, it's defined a little differently. Remember that we not only need an equation that is in terms of the previous term, but we also need to know the seed value. I kind of want to take a moment here to clean up this over here. Bear with me a second. Okay, I kind of like this a little better. So just to be clear, the explicit formula is this guy right here. Okay, this is how we're going to write our equations. This over here is just kind of showing you how to find the d and a sub 0. Up here, I'm just kind of showing you, what you should be kind of thinking about. Okay, you already know a lot about linear functions. So if you just apply what you know about this to the sequence notation, you should be good to go. Okay, so let's now look at our recursive formula. So the recursive formula, you need to know a seed value. Okay, so a sub 0 is my seed value, and you're going to calculate it exactly like we did for the explicit formula, which is you're going to take the first term and subtract the common difference. Okay, so this is known as the seed value. Okay, not really part of the sequence, but it kickstarts the sequence. And then to the way that we're going to write the recursive equation. Now think about what's going on in an arithmetic sequence or a linear function. So in a linear function, you usually think about the slope as being like the amount that you're adding for every unit increase in x, your rate of change. So like if you look at a table, for instance, you are adding the same amount every time. Or if this is negative, you'd be subtracting the same amount every time. So that's exactly what we're going to do, is we're going to add the same amount to the previous term, or subtract the same amount if it's negative. So the way to write this is we're going to write a sub n equals a sub n minus 1, which would be the previous term. Okay, so I know that notation looks a little funky, but that's all it means. Like, so if I want to know what the value of a sub 3 is, the third term, then I'm going to take the second term and I'm going to add the common difference. Or if the common difference is negative, you subtract it. And so the recursive formula is that. Now, d and a sub 0 still mean the same thing as they did with the explicit formula, but just know that you have to write two statements for the recursive formula. The explicit formula, you really only need one, this guy right here. Okay, this is just how you calculate it. But for the recursive formula, you need both of these. Okay, you will not have a complete answer without that seed value. So let's look at a couple of examples of how to write equations of arithmetic sequences. I think it will start to make a little bit more sense as we go through some problems here. And then we'll look at a second type of sequence. Okay, here's example 1. Write a formula for the sequence 2, 9, 16, 23, 30, etc. The first part of this, we just talked about what an arithmetic sequence was, but in general, if I just give you a sequence like this, I'm usually not going to tell you it's arithmetic up front. So you want to be able to identify that it's arithmetic without me having to just spell it out for you. So the question here is, how do we know that it's arithmetic? Well, we have a common difference. There is a common difference. And what is that common difference? How do we know there's a common difference? Well, if I subtract each term by the previous term, I will get the common difference. And if it's the same every time, then I know that, that it's arithmetic. So the common difference here, let's see, from 2 to 9, I have to add 7. Let me scroll down a little bit here. And to get from 9 to 16, I have to also add 7. To get from 16 to 23, I have to add 7. And then finally, to get from 23 to 30, if I add 7 again, then I know I've got a common difference. So that amount that you're adding or subtracting has to be the same for every successive term. And if it is, that is your common difference. So the common difference here is 7. Okay, let's identify the a sub 0. So notice, like, this is a sub 1. Okay, so let me actually write that out. So this is a sub 1. Is 2. Okay, a sub 2 is 9. A sub 3 is 16. Oops. A sub 4 is 23. Y'all bear with me. I know I'm going kind of slow right here, but... And then finally, a sub 5 is 30. Okay, So there really isn't an a sub 0 because your domain has to only be positive integers. But if there was an a sub 0, it would be the term that comes right before this. So to kind of figure out what that would be, just look at our pattern here. To get to the next term every time, we're just adding 7. So to go to a previous term, I would subtract 7. Like if I'm going from 30 to 23, I subtract 7, minus 7, minus 7, minus 7. To get to that, what we're going to use as the seed value, we want to subtract 7. So that a sub 0 is going to equal that first term, a sub 1, minus the common difference. Right? That's the formula that I gave you on the previous slide. So a sub 0 is going to equal that 2 minus the common difference, which is 7, and we get negative 5. Oop, not 0.5, we got negative 5. So the a sub 0 here is negative 5. Now we're ready to write the explicit formula, which, if you recall from the previous slide, looks like this. Actually, I'm just going to copy this, and I'm going to paste it down here. It's the so now I'm just going to fill in everything that I know. So I know the common difference at this point is 7, and I know my a sub 0 is negative 5, so I'm going to change this to a minus 5, and there you go. We've got our explicit formula. Now we can test this, and I do recommend you do this, maybe not every single problem, but most problems. I mean, it doesn't really take any time to pull up your calculator and type in the equation that we're looking at, which is 7n minus 5. So I go over here, 7n minus 5, and just look at the table and see if the sequence is in fact the same. So let me move the calculator out of the way. So you can see that we have 2, 9, 16, 23, 30, and we can even go past that if we needed to. So this is just a way to check and make sure that your explicit formula is correct, which it looks pretty good. So now let's think about how to write it recursively. Okay, so a recursive formula starts with a seed value and then plugs in every previous term to find the new term. So let's first say what the seed value is. And we already figured out what the seed value was, right? We already figured out it was negative 5. So we have to include that. All right, that is required that you identify the seed value for the recursive formula, because otherwise, like I explained before, you're not going to know what it is. So the recursive formula is going to look like this. After you establish your seed value, we're going to take the previous term, which will start with negative 5 as our 0th term, if there was such a thing, and then we are going to do what? We're going to add 7. So we're going to add 7, which is our common difference, and that should work. So like if a sub 0 is negative 5, if I add 7, I get 2. If I add 7, I get 9. Add 7, I get 16, and so forth. So this is the way that we're going to write a recursive formula for this sequence. So that's one example here, right? I give you a sequence, and you can give me the explicit formula and the recursive formula that would generate that sequence. And this is specifically an arithmetic sequence because it has that common difference. Let me show you another example where I don't give you the whole sequence, but instead I give you two terms of the sequence. Now, the way that this question is worded, you do have to know that it's arithmetic, because if I just give you two sort of random terms and say it's in a sequence, that's not enough information to determine whether or not it's arithmetic, if there is a common difference or not. So in this like sort of style of questioning, I have to tell you up front, hey, this is an arithmetic sequence, so that you know kind of what to do. So it's an arithmetic sequence. It says the fourth term is 20. So what I can say is, let me copy this. It's just way easier than having to go through all that subscript stuff again. If I say that, so a sub 4 is 20, and that's just how we're going to like write that mathematically. And it says the 13th term is 65. So I know that a sub 13 is 65. So I have the fourth term, I've got the 13th term, and I don't know any of the terms in between or before or after, but as long as I know that it's arithmetic, I can find all these formulas without too much trouble. So the way we're going to find the common difference is really the same way that you would find slope if it was a linear function. It's the change in y over change in x. In this case, the change in the value of the term divided by the change in the term number. So D will equal, and I'll just copy this real quick. I think this formula kind of overcomplicates it a little bit, makes it look a little bit more complicated than it needs to be. But we want to do a sub 13 minus a sub 4 over 13 minus 4. Okay, in other words, I think an easier way of sort of comprehending it is if you have a sub 13, which is 65, minus 20, this is going to look a little bit more like what your slope formula looks like, where you just actually plug in the numbers. Okay, so it's 65 minus 20 over 13 minus 4. And I'm going to throw that in the calculator here. Set up a little fraction. We got 65 minus 20 over 13 minus 4. And we get 5. Okay, so our common difference here is 5. Now let's identify what the seed value needs to be. Now this can be a little trickier because we don't know what a sub 1 is, but we can still find it. It's not too big a deal. Let me get this calculator out here, at least momentarily. So here's how you're going to find that a sub 0 algebraically. We're going to start by actually writing what we know about the explicit formula. So we know a sub n equals dn plus a sub 0, right? So, dn plus a sub 0. So if we plug in everything that we know, we can actually solve for a sub 0 this way. What we can do is pick one of these points. So like I would just pick this, a sub 4 is 21. Say, okay, well, I know that a sub 4 is 20. So when n is 4, the value of the sequence is 20. So 20 equals, I already calculated the common difference over here was 5. So 5 times term number 4, n is 4, plus a sub 0. And now you can see that we just basically have a little linear equation to solve where we can actually get a sub 0. Oh, this one actually is not going to be as interesting as I thought, because check this out. This is just going to be 0. That's not always going to happen. It usually won't happen that way. Just the way this one turned out. So yeah, if I subtract 20 from both sides, I get 0 equals a sub 0. That is pretty uncommon. Don't expect that the seed value will always be 0. It just happens to be 0 in this case. So, okay, no big deal. Now that we have all the information we need, we can now write the formulas. So to write the explicit formula, we're going to use that dn plus c business. Actually, we already wrote most of it up here. We're going to use this as our format. Okay, here's our explicit formula. We know d is 5. We know this is 0, so we really don't need to put that. Okay, I'm going to put it here just temporarily, just so we don't kind of lose track of the fact that there is that a sub 0 there. I'll go back in and delete it at the end, but leave it there just temporarily. For our recursive formula, we have to define the seed value. Okay, so the seed value, this a sub 0, is 0. And then we would define this as the previous term. So I'm going to go ahead and steal this up here, except I'm going to change what I'm adding. So I've got the previous term plus 5. Okay, so we've got our explicit formula and we've got our recursive formula. And again, now that we've kind of established what these are, I'm going to clean up this explicit formula real quick. We don't need the plus 0 in there, so I'm just going to write it as 5n plus, just 5n. Can I do that? Nope. It's just going to be a big old box there. I guess I could try to center this, but who cares, right? Okay, so those are two different examples for writing explicit and recursive formulas of arithmetic sequences. One case we saw is we have the actual sequence, and another case is I just give you two terms in the sequence and you kind of find it from there. So we're going to kind of use these two examples to examine another type of sequence, and we're going to work these same types of examples for the next type of sequence that we will look at. The second type of sequence, what we're looking at today, is called a geometric sequence. And a sequence is geometric when it has a common ratio. So the arithmetic sequence had a common difference, where if you subtract the consecutive terms, you would get the same number. A common ratio means that if you divide the consecutive terms, you get the same number. So in other words, like if you're moving forward in the sequence, instead of like adding the same amount every time, in the geometric sequence, you are multiplying the same amount every time. So you can kind of think of it like an exponential function, where you have this, this sort of number that you're multiplying over and over again, and that number is going to be called the common ratio. So just like how I told you to think of linear functions when examining an arithmetic sequence, I want you to think of exponential functions, okay, when we're talking about geometric sequences. And so the exponential function here is going to be, you know, if we didn't have any restrictions on the domain, we would say, okay, f of x equals, and then our sort of generic format for an exponential function would be a, which would be our y-intercept, times b to the x, right? So where a is our y-intercept, again, that's the value of the function when y is 0, I'm sorry, when x is 0. And then the b is your multiplier. So instead of having like your slope or rate of change, this is your constant multiplier. So in other words, it's the number that you're multiplying over and over again, right? And you know, you've learned a lot about exponential functions. I think you pretty much cover it a little bit in every single math class, except with the exception of maybe geometry. So you should be pretty familiar with this one. Okay, so this is like the generic form of an exponential function. This is not the explicit formula for a geometric sequence. But it is very similar. So just like how I showed you y equals mx plus b to kind of give you an idea of what this is going to look like. Oh, I misspelled multiplier there. Doesn't like it. I'm going to give you the equation that's going to be very similar to this, but with the sequence in mind. So let's go ahead and, without waiting too much longer, give you the actual formula. So we have a sub n equals a sub 0. Remember, that's that y-intercept, so that's going to be basically like this seed value, like we had in the other one. That's going to play the role of that, you know, that y-intercept times our multiplier, which we're going to call r, okay? R being the common ratio. So this right here is what I mean by the common ratio. It's that number that you're multiplying over and over again. Okay, I just wanted to take a moment to clean that up like we did the last one. So this is our formula. This is our explicit formula. And so now let's talk about the recursive formula, which is going to be kind of similar to what we did before with the arithmetic recursive formula. So before we had a seed value, and then we just added, you know, we started with the seed value, and then we added the common difference to the previous term. So this is going to be very similar to what we're going to do with for geometric sequences, except instead of adding the same amount every time, we are going to be multiplying the same amount every time. So I'm just going to copy this over and just change what I need to. Now here, instead of subtracting d to get back to that previous term, we are going to divide by d, and not d, I'm sorry, the r in this case. So let's change that to a division symbol. There we go. There we go. And then instead of d, we have r. Okay. So what you do is you basically take the previous term, and instead of adding the common difference, you are going to multiply. Do I have a multiplication symbol in here? I don't think I do. Oh, that's interesting. We're going to multiply by r. So we're going to say like times r, and I'll just write this oh, there we go, that looks nice, times r. Now usually you're gonna put the r up in the front because this right here is kind of your independent variable, and usually we put the coefficient in the front. So instead of saying times r here, I'm gonna throw that r over here just so that we don't have to move things around every single time. So we'll say r times the previous term. And you don't have to include that dot, I'm just trying to make it more obvious what's going on here. So those are the two formats for our geometric sequences. So just like we did with the arithmetic sequences, let's look at a couple of examples and see how this will play out. So example 3 says write a formula for the sequence, blah, blah, blah. So the first thing we want to know is, hey, is this actually geometric or not? So the way to test that is to see if you have a common multiplier, a common ratio. Am I multiplying the same thing every time? And I am. So I'm multiplying by 2. Oh gosh, that's ugly. I'm going to have to type that out. I don't feel good about that at all. So we've got times 2. Let's just move that over just a tad. And then we'll just copy and paste this over and over again. Because what's going to happen here is every time that we, let's see, let's get rid of that. Oh, nope, didn't like that. Sorry. You guys, one of these days, I'm going to get a lot better at this. Okay, so we're going to multiply by 2 for each one, right? 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48, and so on. So since we're multiplying the same amount, we know that it's geometric. How do we know the sequence is geometric? Because there is a common ratio, okay? In other words, like 6 divided by 3 is 2. 12 divided by 6 is 2. 24 divided by 12 is 2, and so on. So that ratio of a term divided by its previous term is the same every time. So that is going to be our common ratio. Our common ratio is 2. And our a sub 0 would be the term that comes before the first term. So the way the little formula I gave you to kind of calculate that is up here. It's you take the first term and you divide the common ratio. And so the first term here would be 3. The common ratio is 2. So 3 divided by 2 is 3 halves. Okay, 1.5. Now I don't really care if you write it as a fraction or a decimal. They're both, if you can write it as a decimal, that's fine. Personally, I prefer fractions, but that's just kind of a personal preference because, not every fraction it can be written nicely as a decimal, and there are lots of numbers that can't be written as decimals. So there's some flaws with the decimals, but fractions are usually the way to go. Personal preference, but again, if you can write it either way, I don't really care. So the explicit formula here will be written like this, and now that we know what those objects are, or what those parameters are, this should be pretty easy to take care of because we don't have to actually find anything. So a sub n equals a sub 0, which we said was 3 halves, and then times the common ratio, which is 2. That's it. It's that simple. Okay, so as long as you can identify the common ratio and a sub 0, which is our seed value, we've got it. The recursive formula will be written very similarly. We've got our sort of format up here. I'm just going to copy and paste it, just because we have to have that seed value. We have to have that in order to kickstart the actual recursive sequence. So we've got our a sub 1, which is 3. Oh wait, we already calculated a sub 0. We don't need to do that again, right? It's 3 halves. So that's our initial term, and then we'll take, to get the next term, we are going to multiply by 2. So we've got 2 times 3 halves, which is 3. 2 times 3 is 6. 2 times 6 is 12. 2 times 12 is 24, and so on. So you're taking that previous term and then multiplying it by 2. So we've got the explicit formula and the recursive formula. So that's one example. Just like with the arithmetic sequence, we started with kind of the easier one of the two, which is if I just straight up give you the first few terms of the sequence, you can write the formula that way. The more challenging one, just like with the arithmetic sequence, is when I give you 2 different terms and I don't give you the whole sequence and ask you to write the formula that way. So let's see here. The third term of a geometric sequence is 18. So we can say that a sub 3 is 18, and the sixth term is 486. Now, just giving me two terms is not enough information to determine whether or not it's geometric or arithmetic or some other kind of sequence. So that's why in the problem it says specifically that it's geometric. Without that information, if all you have is two terms, not enough info to actually establish the sequence. You do need more than that. So, okay, so we know it's geometric because it says it's geometric. So let's try to find the common ratio. Now this is a little trickier, but I'm going to try to talk you through it. So if we know that the third term is 18, and we know the sixth term is 46, and we know it's geometric, what that means is we are multiplying some number, over and over again until we get to 486. So the question becomes, how many times are we actually multiplying it to get from here to here? So the setup here is to say, okay, well, I'm going to multiply 18 by that common ratio, okay, so times that common ratio, however many times I need to. Now let's think. If I multiply it one time, that'll take me to a sub 4. If I multiply it two times, that gets me to a sub 5. And if I multiply it one more time, that should take me all the way to a sub 6, which is 486. So the number of times you're multiplying by the common ratio is the same as the difference between the term numbers. So notice like there are 6 minus 3 is 3. That's how many terms exist in between here. And so that's how many times we're going to multiply that common ratio. Now there's an easier way of writing this so that we can actually solve it. And that is, we can write it as, if I have r times r times r, that's really the same thing as r cubed, okay? Now, if I were to give you like the eighth term, you'd have to multiply r 5 times, right? r times r times r, all the way till whatever it is. So that number right here is going to be how many times you have to multiply, which will be the difference between the term numbers, okay? So like if I give you the second term and the 10th term, you'd have 8r there, because 10 minus 2 is 8. And this number right here would be 8 as well. So, so now we can actually solve for the common ratio. I'm going to divide both sides by 18, which I'm not going to pretend that like I can do it in my head. I'm going to pull out the old calculator here. Well, I guess you should see it too. I've got 486 divided by 18, and I get 27. Okay, so now I've got an equation that says r cubed equals 27. Let's get out of that exponent. And, well, how do I solve for r here? Well, I just take the cube root of both sides. Or, in other words, raise both to the 1/3 power, and that'll cancel this out. So r equals 27 to the 1/3 power. Okay, or the cube root. You could write it either way, honestly. If you want to write it like that, that's fine. If you want to say, I wonder if this, am I even going to be able to do this in here? I've never actually tried this. Oh, yep, looks like we got that option. Sweet. Okay, so you can write this in Cami. That's pretty cool. Either way is fine. I mean, these mean exactly the same thing. So whichever way kind of makes more sense to you, just write it that way. You don't have to write it both ways. But this is, again, something, this one's kind of easy to do, relatively speaking, in your head. But just to be safe, I'm going to use the calculator. So I have got 27 to the 1/3 power, or I can write it as the cube root. Let's see, how do you do cube root in here? I think it's math. Yeah. So I can do the cube root. Well, let's change that. The cube root of 27, and you'll see you get the same thing here. Okay, so it doesn't really matter which one you do, but either way, r is 3. So that's our r value. That's kind of the trickiest part about this, I think. We can find a sub 0, kind of like how we did the arithmetic sequence, where we set up our explicit formula. So we got a sub n equals, there we go, equals r times, oh, I'm sorry, a sub 0, wow, I'm slipping. A sub 0 times r to the nth power. Okay, so if we know r and we know one of the terms, we can solve for a sub 0. So I'm just going to plug, I like to use the smaller numbers just so my values don't get crazy, but it doesn't matter which one of these coordinates you pick. I just like the smaller one. So I'm going to plug in 3 for n. Say the third term is equal to 18. I know my r is 3, so now I can just solve for a sub 0. So 3 cubed is, pretty sure that's 27, but here, let's, just to make sure, 3 cubed is in fact 27. Yeah, okay, so we're good there. So we've got 18 equals a sub 0 times 27. Okay, and then so we just need to divide both sides by 27. So this is not going to work out as a whole number. So let me, oh geez, you can't see what I'm writing. Oh gosh, I'm so sorry guys. I got to get better about that. Anyway, so let's go ahead and divide this. Now I'm going to actually write it as a fraction, but I'll show you how to get the fraction otherwise. The nice thing about doing this is it's going to reduce for you, and so we get 2/3. But let's say you just typed it like this, 18 divided by 27, you get the fraction. We don't really like fractions, especially ones that go on forever like this. I don't like decimals rather. So to convert it to a fraction, you hit math, and then you just hit enter, and then it'll give you the fraction. So my seed value is going to be 2/3. All right, so we got the common ratio and we got a sub 0, so the hard part's done here. Now we can just go ahead and write our explicit and recursive formulas, which were given up here, right? This is going to be the format, so I'm just going to copy and paste. Actually, can I just get all this at once? That'd be kind of nice. Yeah, there we go. Oh, it didn't give me the seed value, that's fine. Okay, well, I guess we're going to have to move these around. That's no big deal, no big deal. Okay, so the, and we don't really need all this, do we? No. All right, well, it doesn't really like that. Okay. There we go. Okay, so our seed value, or a sub 0, is going to be 2/3. My common ratio is going to be 3, so here we go. And let's, before we, we're almost done here, but I think it's worthwhile just one more time. Let's type this in to y equals and just make sure I'm getting the right sequence. So 2/3, oh gosh, calculator, in the way. Okay, anyway, 2/3 times 3 to the power of x. And let's check those two terms they gave us up front, right? It said a sub 3 was 18 and a sub 6 was 46. So if I look at the table, just to make sure my sequence is right here, the third term is 18, the sixth term is 46, so we are in business here. Okay, I'm just going to get rid of this calculator. I don't think we really need it from here on out. Okay, so there's our explicit formula. We're done there. For our recursive formula, let's move this out of the way a little bit. We need our seed value, which didn't get copied over for some reason, but I can just copy it over from here. Okay, that is a requirement for all recursive formulas. You do need a seed value. And then, so we're going to take the previous term and just simply multiply it by 3, and we're done, right? We're going to take, and we can see that in the sequence. This one didn't give us a sequence. But if we were to multiply this thing by 3 over and over again, we would get 46. So that's it for today. So basically, just to recap here, we went over 2 different types of sequences: arithmetic sequences, which has a common difference, and geometric sequences, which has a common ratio. They're similar to a linear function and an exponential function, and we went over 2 different ways of writing the formulas for these different sequences. We went over how to write them explicitly and how to write them recursively. So basically 2 different types of sequences written 2 different types of ways. So that's it for today. Next time we'll get into something called a series, which is what you get when you add all the terms of the sequence together. So let that percolate in your brain a little bit, and I'll see you next time.